Welcome back. Now we're going to take a look at the high frequency response for a common emitter amplifier circuit. And again, that's just in general terms, not a particular example, so I haven't entered any values. So we're just going to come up with general expressions. But again, the important thing is that you get familiar with the process of determining, what are the capacitances that you need to consider, how do you calculate them, how do you calculate the Thevenin resistance across those capacitances. So high frequency response for this common emitter amplifier is just the same one from the previous example. Now, in order to consider the high frequency response, I'm going to go ahead and draw the AC equivalent circuit, just so that we're properly ignoring the coupling and bypass capacitors, as well as DC sources and things like that. So let me go ahead and, so this will be VS. So you could call this my high frequency equivalent circuit, I suppose. Then you have, so this is RS, this is the parallel combination of R1 and R2. I'm going to combine them since they're both going to signal ground. Then I have my BJT transistor. At the collector I have resistor RC connected to ground. I'm shorting through the coupling capacitor. This is RL. This is CL. That's V out. And then in case of my emitter, I am shorting through CBE, and so it's just a direct short to ground. Now let's go ahead and include the capacitances that are going to play a role in our high frequency response. I've already included CL. And then we're going to have, I'm going to draw them in orange because I'm going to be sort of modifying them a little bit later. But we have, if you remember, CBC and CBE, right? CBE is simple. It's just a capacitance between the base and ground because the emitter is directly connected to ground. So I'm going to go ahead and just replace that with CBE to ground. Now this CBC capacitance is a feedback capacitance in this case because this is a common emitter amplifier. We're applying the input signal at the base, we are taking the output out of the collector, and that capacitance happens to be connected between base and collector, between input and output, and is therefore a capacitance in the feedback path, which is going to be affected by the Miller effect, meaning that capacitance is going to appear as two shunt capacitors, one at the input, one at the output, of values. The one at the input is going to be multiplied times the gain of the amplifier. The one of the output is going to have approximately the same value as CBC. So I'm going to split that. I'm going to call this one, in order not to crowd my circuit here, Miller input capacitance. And the one at the output is going to be Miller output capacitance, CM output. So I'm going to delete this one since I've replaced it. Oopsie. All right, so this will be my, my high frequency equivalent circuit now. And I'm in a good position to start considering my high cutoff frequencies. I'm going to consider first the one due to the capacitance connected to the base, and then the one, or at the input, and then the one due to the capacitance connected at the output. Now, you may say, well, there are 4 capacitors here, and I just noticed I wrote CL as a resistor, but that's actually a capacitor. You may say there are 4 capacitors here, shouldn't we have 4 high cutoff frequencies? But notice that, they're connected in parallel with each other, so CMI is connected in parallel with CBE, so the parallel combination of the two is just going to be equal to an equivalent capacitance of value equal to CMI plus CBE. In other words, I can combine these two capacitors as just being one capacitor value C Mi plus CVE. And the same happens with CMO and CL. I can just combine them, and the parallel combination of two capacitors, the equivalent capacitance is equal to the sum of those capacitances. So in all reality, you can see I have just two capacitors. So let's go ahead and consider FH1, which is going to be due to the input capacitance. So I'm just going to label it FHI for input. This is going to be equal to 1 divided by 2 pi R Thevenin I will call it, CI for C input capacitance. Where I have already determined that my input capacitance is the sum of the Miller input capacitance and CVE. And the Miller input capacitance is going to be equal to CVC times 1 minus A plus CVE, are approximately equal to the absolute value of the gain times CVC plus CVE. And the reason for that is the gain for a common emitter amplifier is typically much larger than 1. My R Thevenin input will be the equivalent resistance connected across the terminals of that capacitor. So if we look at our high frequency equivalent circuit here, we will see that we have R1 in parallel with R2, and all that in parallel with RS. And again, I am turning off my voltage source VS, so that's just a short to ground. So it's basically R1 in parallel with R2 in parallel with RS. That will be the value. Oh, and I'm missing one. And the one that's connected on the other side, which is going to be beta times little re. And now I think I've got all of them. So that will give me a value for high cutoff frequency FHI. I can reproduce that methodology for my output capacitance and come up with another high cutoff frequency to the output capacitance. 2 pi R Thevenin seeing across the terminals of the output capacitance times the output capacitance, where my output capacitance is the combination of the load capacitance and the Miller output capacitance in this case, so CMO plus CL. And CMO is going to be equal to 1 minus 1 over A times CVC plus CL. And again, since the gain is typically much larger than 1 for a common emitter amplifier, we can approximate this as CVC plus CL. And now the Thevenin resistance across the terminal of that capacitance is just going to be from the schematic or from the drawing, RL in parallel with RC, and if we want to consider little rho, it will also be in parallel with little rho. So RL in parallel with RC in parallel with little rho. And then I have two values for the two frequencies where I have my two poles, the one introduced by the input capacitance, the one introduced by the output capacitance, and I can consider my overall FH to be equal to the lowest or the minimum between the two, FHI, FHO. Now, if you're a little bit confused as to the process and how we came up with some of the resistances and so forth, don't worry, just keep going, because we're going to see several examples with actual circuits, common emitter, common base, common collector, and I think that by doing a few of them in actual examples with actual values, hopefully you'll get the hang of it. So, thank you.